Back on. All right. So, thank you for at least trying with VoiceThread. I know it was to put it in mild terms, a huge pain in the ass. I apologize for all the emails or all the announcements trying to figure out what the issues were. I think I narrowed it down to at least a couple. So I want to point out a couple of things real quick, and then just show you a couple of things that I added this morning. So I put up a new small video. It should link you straight to, oh goodness gracious, should link you directly to a YouTube video on how to actually create these and then share them with your group. So I can kind of walk through that here. If I'm not mistaken, actually, I think that these are set up. I had a couple of people email me on Wednesday or even yesterday, like, do I have to wait for all my group members to respond before I hit submit? I think the answer actually is no. So I'm going to use one group as an example real quick. Brendan, who are you grouped with? I can't remember.
Group for Alan. How do you pronounce your name? Kaylin? Okay. Kaylin, Olivia, and Grace, whoever she is. Grace.
Okay, so who created that one? Kaylin, did you submit it before like 5 o'clock yesterday or something like that? And Brendan's posted afterwards. So I think actually whoever creates it can actually upload a file right away, hit submit, and you can continue to add to it afterwards. So you don't have to wait until 11 o'clock at night to submit them. So that's a first issue that I think I was wrong on originally when I was commenting on it. So just get them submitted right away. You can keep adding to it as you go along. Okay? The second one is when you're sharing, you want to make sure that you share with the group members in a way that in the future, not only you allow them to view and edit, but also, view and comment, but also there's an option to allow them to edit as well. And later on, when we do these where you're working on like putting together maybe 2 or 3 slides, you want to make sure to share that option as well so that everybody can add files to it. The other one that I noticed that I forget about, if your browser is one that doesn't allow third-party cookies, you need to change the settings for that. And then the last one, and I don't know why the heck this is an issue, but it is. I'm just going to open up one of these real quick. So I just created this practice one. It's no point. It's just a way for you to kind of practice uploading these. This is what I see when I get your responses. So usually it moves you from, at least whoever created it. Oh God. Okay. From down here to up here. And the one thing I want to point out real quick about this, I know some people were having issues yesterday where they were clicking in on this and then hitting that launch button. If you do it, it denies you. You need to let it automatically load on its own. So just by clicking that initial link, getting to this page, if I just sit here now and wait a few seconds, it's going to upload on its own. And I think that was an issue that some folks were having. They were clicking that launch button and then just not being able to access it at all. Is there anything I'm missing right now? Who wasn't able to at least try to get in at least get in at some point? I know I didn't see comments from everybody, and that's fine for this first one. So what I'll ask is for those people, I still want to get to know folks in this classroom, and that was part of this activity, was just for me to get to know everyone. Emily, right?
Yes. How do you submit it?
Ah, good question. So whoever creates it, I'm fairly certain there's a button in the top left-hand corner where there's a submit option. Somebody who submitted one. Am I? It's in the bottom?
Like middle, bottom, right-hand side.
Middle, bottom, right-hand side. So completely opposite of where I was saying. There's a submit button where you can submit these. Okay. Claire.
So just the group creator has to submit it, not every individual person?
Yep.
Okay.
Just the group creator. And if you upload, whoever creates it, if you just right away create it, upload any file into there. Let me see if there's anything else I need to cover with that right now. So at the end of class today, what I'm going to do with the last like 5 to 10 minutes is talk about the next lecture assignment and then talk about the lab assignment for Tuesday real quick as well. So make sure, if I lose track of time, somebody please stop me. But let's get started just kind of rehashing the topic from overnight. Hydrophilic versus hydrophobic. And I think a lot of people got some basic characteristics. Hydrophobic means what? If we were to define or to describe hydrophobic? Exactly. So water repelling, water fearing is hydrophobic. Hydrophilic, water loving. And these come from properties of the molecules themselves, right? So for example, let's say that I have, oh, no, I don't want to erase. Sodium ion, Na+. Why is this hydrophilic? Okay, so it has a charge. It has a positive charge on it, which is a really key characteristic, right? And most hydrophilic molecules either have full charges or they have what we call partial charges. So for example, if we drew something like ethanol, since it's simple, in here, there are some polar covalent bonds. And what do we mean by polar? What are some qualities of a polar covalent bond? How are the electrons shared? Equally or unequally? It's unequal. So they're pulled more towards one atom over the other. And what determines which molecule those electrons get pulled towards is based on electronegativities. So oxygen, of the four that we'll talk about most commonly, oxygen, nitrogen, carbon, and hydrogen, oxygen is the most electronegative. In other words, it holds on to electrons more tightly than any of the other four. There are on the slides some electronegativity values, and I'll pull those up in a couple of minutes. I'm not expecting you to memorize them by any means. But what I am expecting you to be able to do with them is if I ask you, is a bond between, for example, carbon and hydrogen polar or nonpolar, you actually either have, one, memorize that, or two, know how to calculate whether the bond is polar or not. So we'll come back to that in a minute. But I do want to point out that in this one here, we've got this carbon-oxygen bond is polar, and then the oxygen-hydrogen bond is polar as well. And oxygen, again, being the most electronegative, it's going to pull those electrons towards it. And so what we say is that oxygen has a partial negative. This isn't an S, it's actually the Greek letter delta. So that's one way we can signify partial charges. What does that mean for the hydrogen then? If its electrons are being pulled away from it, what's it going to be left with? Partial positive charge. So hydrogens get partial positive. And again, in this case, this carbon here bound to the oxygen would have a partial positive charge as well. So what does that actually mean? Well, it means that the electrons being closer to the oxygen are unshielding that atomic nucleus, and so the protons that are at the center are kind of starting to give off a little bit of charge there. These aren't as strong as full positive and full negative charges. I like to think of them more like electrostatic interactions, kind of like if you have a partial positive and a partial negative interacting with each other. It's like two magnets attracting to each other. So let's take a look at how this works in principle. I'm going to skip to electronegativity real quick, and then we'll come back to how this works with water. Here are those electronegativity values. So oxygen is 3.5, nitrogen is 3.0, carbon is 2.5, and hydrogen is 2.1. We consider differences equal or greater than 0.5 to signify a polar bond.
So, using that as a guide, a nitrogen-hydrogen bond. What's the difference between in their electronegativities? 0.9. Is that greater than 0.5? Yes, it is. Polar bonds between nitrogen and hydrogens. How about between oxygen and nitrogen? It's equal to 0.5. We would consider this to be polar. I usually kind of say it, though I put the caveat that it's weakly polar. So these are really minimal partial positive and partial negative charges. Which ones would not be polar? So which of these up here, when bound together, would not create a polar bond? Derek? Great. So anything equal to any atom bound to itself obviously would have a nonpolar covalent bond. What else? Kaylin? Hydrogen and carbon. And that right there, the absence of difference in electronegativities, the absence of those partial positive and partial negative charges, that's what leads to hydrocarbons being hydrophobic. Because those partial positive and partial negative charges, that polarity contributes to hydrophobicity or hydrophilicity of molecules. Okay? So let's take a quick look at how this interacts with water then. But I'm going to pause real quick and see if there are any questions on this principle. Okay. So here's an example of water molecules. You may have seen this one in the video. Obviously, we've already established that oxygen-hydrogen bonds are polar. So in this case, oxygen has partial negatives, hydrogen have partial positive charges. And we can get hydrogen bonding within water. That's what gives water properties of cohesion, adhesion, the ability to dissolve molecules. The way that we indicate these hydrogen bonds that form between partial positive charges of hydrogens and partial negative or full negative charges of other molecules, atoms, would be with a dashed line. Okay, and these again are just electrostatic interactions, kind of like a positive and a negative charge on a magnet coming together. Not as strong as ionic bonds, definitely not as strong as covalent bonds, but very important when we start to talk about metabolism and also some other properties that come up with macromolecules in prokaryotic cells as well. What if I had a cube of sugar? So table sugar is a disaccharide. It's made up of two monosaccharides or monomers of carbohydrates, so fructose and glucose. What happens to sugar when you put it in water? It dissolves. And I want to bring up a really important point here. There's going to be 2 points that I'll make. One, when we say that something dissolves, what do we actually mean? We know that it disappears, right? But what's actually happening on a molecular level here? It disassociates. Do those individual glucose or those individual fructose molecules break apart? And the answer is no. What happens is you get individual glucose-fructose disaccharides that will separate from each other. But it's not as if those covalent bonds break. And this is oftentimes, I'm making a point here to hit on this because this is one thing that in the past I've seen as being a misconception, that folks will think that when something dissolves in water, all of the bonds break. That's not true. Actually, the hydrogen bonds will break so that hydrogen bonds can be formed with water. But the covalent bonds that hold together that sucrose molecule will remain. Okay, and that is just a really important point I want to make sure we address. The other point I want to make here is, so let's take a look at two examples of carbohydrates real quick. So we've got glucose is a monomer. Basically what gives apples, etc., their wonderfully sweet taste. So I'll just kind of sketch real quick glucose. Don't feel like you have to write this. You could just write glucose if you want to. Okay, here's glucose. If I have a bunch of glucose, dump it into a liter of water, it's going to dissolve. Anybody disagree with that? Okay. What are other things that are made out of glucose? Who showered last night or tonight? Or this morning? Not looking ahead to the future. Okay, good. Did you dry off with a towel? A towel is made of what typically? The fabric of our lives, right? Cotton, okay? What's cotton made of? It's glucose. It's a polymer of glucose. It is a highly branched polymer of glucose. When you dry off with your towel, does your towel dissolve? Thank the Lord, no, right? Because then we'd be spending lots of money on towels, and I don't think anybody would. Anyway, they don't dissolve. Why not? So it's made of glucose, just like the sugars that we find in apples and other fruits, but why doesn't a towel dissolve? It's hydrophilic. It's got polar bonds. Anybody want to take a guess? The simple answer is it's too big. It's too bulky. In fact, these the sugars, I'm just going to now draw glucose as circles here. But we find that these polymers are so highly branched, so highly complex and large, that water actually can't fit around it in a way to create what we call a hydration shell. In other words, even though it's forming hydrogen bonds with it, it can never create like a cloak. If any of you are into Harry Potter movies, I know some people were talking about that in their videos. So he's got a little Harry Potter's got a cloak that he uses to hide. That's kind of exactly what water does when it dissolves molecules. It basically masks that molecule so that you can see around it. Can't do that with large, bulky objects like cotton. Okay? So one of the points that I usually try to make is that with hydrophilic molecules, they can be dissolved in water. But it doesn't necessarily mean that they will be dissolved in water. Size here is a really important characteristic. Another important characteristic is if you keep adding sugar to water, at some point that water solution becomes saturated. The sugar will now no longer dissolve. So amount has an important factor in this as well, or concentration. Any questions? All right. Let's do this. Either by yourself or with somebody else. I don't have a preference here. What I'd like you to do is describe to me the relationship between pH, acid, base, and hydrogen ion concentrations. If you feel comfortable with that, add buffer in there. All right. I'll give you a couple of minutes to work on this before we discuss as a group. To those thoughts for a second, I forgot to cover this question I asked. Carbon, hydrogen, oxygen, and nitrogen. How many bonds can each of these form, and what dictates that? Anybody know? Ashley, go ahead.
Carbon forms 4 bonds.
Okay.
So it's in its valence outer valence shell that has 4 electrons, and it wants to get 8.
Good.
Full shell.
Perfect. Perfect. So it's already got 4 in its valence shell, needs to add 4 more to complete that octet so it can form 4 bonds. Brendan?
Nitrogen can only hold 1 extra ion because it normally starts out with 1, but its valence shell can only hold 2.
Perfect. Perfect. So hydrogen can gain, so in other words, it can only form 1 extra bond as well. How about oxygen? Given these same principles. Erica?
2.
Perfect. And then nitrogen? 3. Perfect. Okay, I just wanted to make sure we had this down because this is just an important concept that I need to make sure that we cover, especially as we start to talk about these molecules on Monday. Now, back to pH. What's the relationship? Tef.
So like acidic is like 1 through 6, and bases are 8 through 14.
Okay, good. Just to broaden that a little bit, what we could say is acids are anything up to 7, bases are anything 7 to 14, and then neutral is 7, right? What else? Ashley?
pH scale measures the concentration of
It does. And how does that relate? How does the pH actually relate to the hydrogen ion concentration? It's inverse. That's a really key point, Abby. What else? Anybody know the actual mathematical relationship? Who's now tuning me out because I said math? Thanks, Austin, for being honest, at least. It's a log relationship. And I'm not going to get into the specifics of this because it's not entirely important to understand micro. But I think the big thing to note is, as a couple of folks have already kind of alluded to, so here are our acids down this way. As we move towards a more acidic condition, that concentration of hydrogen ions increases. As we move to a more basic condition, the concentration of the hydrogen ions decreases. What about hydroxide ions, OH negative? Derek? It's the reverse. Good. Perfect. Where we really talk about acids and bases is in terms of growth control, actually, in microbiology. Using acids more often than bases is a very common way to control microbial growth. And so we'll come back to this concept a little bit, but what effect do acids have on a cell? Just to kind of give a thinking ahead about this. Anybody want to take guesses? If I put E. coli, for example, in pH 3 solution, what's going to happen? Live, die? It probably will die. It's going to take some time. But how? How does it die? What macromolecules are most affected by changes in pH? Okay, so lipids possibly can be. So our macromolecules that we'll talk about on Monday, fatty acids / lipids, etc., nucleic acids, proteins, and carbohydrates or polysaccharides. What we find is that actually one of these that is maybe I shouldn't say that it's the most affected, but that we focus on most often are the proteins, because proteins dictate function within the cell. And by changing pH, what actually happens is we disrupt the hydrogen ion we disrupt the hydrogen bonding that occurs between water and hydrophilic proteins. And in doing so will lead to protein denaturation. So that's a concept we'll come back to, and actually we'll revisit it on Monday. We'll revisit it about 2 weeks later. We'll revisit it again a couple of weeks after that. You're going to kind of see that happening in this class, where we will come back to themes multiple times. I don't think there's anything else in there I wanted to cover. That was about it. And then the last piece is just buffers, and I'm just going to make a quick note on buffers. As most people would define it, buffers just resist change in pH, and that's absolutely true. The way that they do so is I like to think of buffers like sponges. So if you are holding a sponge underwater, assume that water are your hydrogen ions. The sponge will absorb that water, just like a buffer will collect hydrogen ions. It's actually got free electrons to donate to those hydrogen ions so that covalent bonds can be created. Just like this example here, bicarbonate. Oh shoot, that's gonna, damn you. Please, or not. Okay, well anyway, I'll just, that carbonate, bicarbonate can pick up a hydrogen ion in order to soak up the excess ones. And then at some point, each buffer has a buffer capacity, at which point it no longer works. There are no more free spaces for those hydrogen ions to bond to. And then buffers, as the conditions change, as we need to release water, just like a sponge will release water, a buffer will release those hydrogen ions as a way to donate them to a more basic solution, again, to minimize that change in pH. So those are the basic concepts of that. Okay, I've covered most of everything I want to for today. Are there questions still remaining? Okay, don't close up just yet, because we're going to do one more thing before I talk about the next, before I go ahead and talk about stuff for the future. One of the things that I like to try and do from time to time is to get us to think about how do these ideas connect with each other. Okay? Who's done concept maps before as a way to connect terms? Okay, so a few folks have. What we're going to do is we're going to concept map a set of terms. So I'll write them down real quick. All right, so we are going to concept the terms covalent bond, hydrogen bond, which I'll just abbreviate H bond here, polarity, solubility. You could replace this with dissolves if you want to. Sorry for the cruddy handwriting. Nonpolar, polar, hydrophilic, and hydrophobic. And you may be sitting there going, wait, didn't we just go over this? And the answer is yes, but I talked about it. Now it's time for you guys to try and put this together. Okay? Take what I've said or the lectures or your own thoughts and try to connect these together. Again, the key part of a concept map is not only to connect these, but then to describe what that connection is in between. Feel free to work in pairs, groups, individually. This is not an assignment, but this is one way to mentally organize this information. I'll give you about 5 minutes to work on this. And then if you have questions, please ask.